and I'm thrilled to be invited to give a lecture here. So today I'm going to give a talk on deep neural network, the model compression, and a hardware accelerator engine to accelerate the compressed neural network. A brief introduction of myself and my advisor. So currently I'm a fourth-year PhD student at Stanford, and my research interest is in computer architecture for deep learning to improve the energy efficiency for neural networks running on the mobile and embedded systems. So this recent work on deep compression and energy efficient inference engine has been published in NIPS and covered by the Next platform. And this is my advisor, Bill. So Bill is the professor at Stanford and former chairman of CS department. And he leads our CVA group and also the chief scientist of NVIDIA and holds numerous titles and awards. So this talk, I'm going to talk about two things. The first one is deep compression. So how to compress the large deep neural network models to make it small to run efficiently on the mobile system. And the second part is EIE Accelerator. So it is an efficient inference engine that runs on the compressed neural network model. So let's get started with the introduction of deep learning, the next wave of AI. So on the left-hand side is the human brain, and on the right-hand side is the artificial neural network. So the artificial neural network is inspired by our human brain, that the signal flows from our eyes and goes all the way to the back of our brain. And after the stages of processing, it can recognize from the picture to tell you that this is a cat. So for the artificial neural network, it has an input layer and many hidden layers, and finally an output layer. It tries to construct a highly nonlinear function so that it can be widely applied to applications ranging from image recognition, speech recognition, natural language processing, with applications such as speech recognition and image recognition, machine translation, robotics, surveillance, self-driving, and assistant driving. But with all these interesting applications, what is the problem of really deploying such deep neural networks onto the mobile platform? Say if you want to have an app that runs deep neural networks on your phone, the app developers suffers from the large model size. For example, the previous AlexNet, which is invented in 2012, has a model size of around 240 megabytes. And VGG16 network has a model size about over 500 megabytes. But App Store have the restriction that an item, if it's over 100 megabytes, then you cannot download until you connect to the Wi-Fi. So this is a comment that talking about the importance of model compression, commented by Andrew Ng, saying that at Baidu, the number one motivation of compressing the networks is to bring down the size of the binary file. So as the mobile-first company, and some companies are mobile-only companies, we frequently update various apps via different app stores. So it's very sensitive to the size of the binary files. So if a new feature increases the size by 100 megabytes, it will receive much more scrutiny than one that increases it by only 10 megabytes. So it's very crucial to reduce the size of the neural network model to make software engineers and app developers happy, to put it small enough to put it into the mobile phone. And secondly, our hardware engineers suffers from the large model size. So especially given the limited resource constraint of the embedded system. So what does large model size mean? So large model size means we have to pay a lot of memory bandwidth to run such neural network models. But comparing the energy consumption of different operations, we can see that the memory reference is 2 or 3 more order of magnitude than those ALU operations such as add, multiply, and SRAM cache access. So a DRAM memory access takes as much as 640 picojoules, comparing with only 5 picojoules if we fetch a parameter from SRAM cache. So reducing the model size is very crucial if we want to deploy it on embedded system given the limited hardware resource. On the other hand, what about deploying the neural network on the cloud? So it suffers from these problems. So first, we have a network delay. Say we upload our image to the cloud and then get the result back, given, say, 0.1 second delay. If you have a self-driving car application running on your car, 0.1 second, if you're driving at 70 miles per hour, that is already 10 feet away. And also for power budget. So the power consumption is a major part of the total cost of ownership of a data center. So the power budget is a crucial factor as well. And finally, the user privacy. So companies like Snapchat, they want to preserve the user's privacy and don't want users don't want to upload their images to the cloud and then get the result. So it is if you have some app that say scans your credit card and to know those numbers, you don't want your credit card to be uploaded to the cloud and then get back. So essentially, you want everything to be done locally on your phone. So that motivates us to have an engine that can run neural network and deep learning applications in real time on your mobile devices. So given those constraints, we propose two solvers. The first one is deep compression that compressed deep neural network model size down to a very small size so that it can run efficiently on a mobile. So it has three main features. First one is it has a smaller size. It can compress the mobile app size by 35 times to 50 times. And the second one is accuracy. So although the neural network model is compressed, it does not suffer from an accuracy drop. It still have the same accuracy as the original network. And finally, speed up. So we hope to have the inference running faster and have lower latency running the compressed model. So the second solver is efficient inference engine, which is a ASIC accelerator that accelerates and runs on the compressed model. So it also has three features. The first one is offline. So everything we can run locally on the mobile. So no dependency on the network connection. A second feature is real time. There's no network delay and have a high frame rate. And finally, low power, so that we can have a high energy efficiency and have our battery runs longer. So let's look at the first, the deep compression. So as a highlight, it can compress AlexNet by 35 times, bringing down the model size from 240 megabytes down to only around 6.6 megabytes. And for VGG network, it compressed by 49 times, compressed from the original model size over 500 megabytes down to only 11 megabytes. So both cases has no accuracy loss. So now the weights can fit on the on-chip SRAM, which takes 120 times less energy than if you have to go to the DRAM memory. So how is the deep compression implemented? So it is a pipeline consisting of first we prune the network, and then we enforce weight sharing on the network. So pruning says we remove the redundant synapses from the network. So this is the original network that is densely connected. And this is the pruned network that redundant weights are removed. So next I'll talk about how do we eliminate the redundant connections. And the next step is apply weight sharing. Say this weight and this weight are pointing to the same memory location. So both during inference and during training, they are updated and used at the same time with the same value. And the final step is Huffman coding. It's not on this picture, but I will talk about it later. So let's go through the first one, which is pruning. Pruning is implemented by we train the network like before, and then we prune the connections by finding the absolute value of the weights. If they are small, then we remove them away. And finally, we retrain the weights, and we do it iteratively to recover the accuracy. So after this pipeline, the network can be reduced by 10 times without losing accuracy. So this is a little bit of motivation. It's actually motivated by our human brain. So when we are born, trillions of synapses are generated during the first few months of birth. And then at 1 year old, it peaked at 1,000 trillion. And at 10-year-old, a child has only around 500 trillion connections. So this result has been published by Nature, saying that this pruning mechanism removes the redundant connections in the brain. So we first develop a lot of connections, and then as we grow up, as we learn new stuff, a lot of redundant connections are removed. So only those useful connections, synapses, are preserved. So does this mechanism also work on artificial neural network? So the answer is yes. If you see the results across 4 different artificial neural networks, across 2 different benchmarks, across 2 different data sets, this is MNIST data set, classifying 0 to 9 digits. And this is ImageNet that has 1,000 classes, the largest data set of image recognition. So the network can be comprised ranging from 9x to 13x without losing the accuracy. Some of them even have a less error rate. And this is a detailed result on AlexNet. Through pruning, this horizontal is telling us how many parameters are we removing away. So at this point, we are removing 90% of the parameters in the original network. And the y-axis is the accuracy loss, telling us how many accuracy do we lose by pruning the network. So of course, the more to the right up side, the better the result. So this is the best result, telling us that removing 90% of the parameters resulted in no accuracy loss. So these 4 lines are design space exploration of different pruning methods, including using L1 regularization versus L2 regularization. And the dashed line are pruning the network without retraining the network. So we can see that even without retraining the network, say if you don't have the data set to retrain, you can still get around 50% free lunch by pruning the network. And then an interesting point lies in this line, this green line on the top. We can see that sometimes the accuracy even got improved by finding the right number of model capacity of the pruned network. But if we prune too much, the accuracy will begin to drop. So this technique has recently been used by Hong Kong University. They in NIPS, they used pruning deliberately to increase the accuracy of classifying, detecting phases and classifying phases. So this figure shows how many parameters in each layer of AlexNet and VGGNet are redundant and can be safely pruned away. The green part is like the water that you can safely remove in a sponge. We can see that this is the total parameters, and all of these green parts can be safely removed. And so it is for the VGGNet. Around 93% of the connections can be safely removed without impacting the accuracy. And if you see the breakdown of the convolution layer versus the fully connected layer, so both conv layer and fully connected layer can be pruned, but conv layer can be pruned less, around 3 times, and FC layers can be pruned more, about 10 times. And usually the first layer that directly interacts with the input image have less redundancy generally for both networks. So let's see what exactly does pruning do, and what is the pattern of the pruning network. So this is a very basic illustration of on the MNIST dataset that has digits 0, 1, 2, 3, all the way to 9. So this is the LANET 300, 100. So the first, and this is the sparsity pattern of the first fully connected layer of LANET 300 and 100, which is a fully connected neural network, classifying the digits. So the input image has 28 by 28 pixels. So altogether 764 pixels. That's the input. And the hidden layer, first the hidden layer have 300 elements. So the first matrix of the network is basically a 764 by 300 matrix. So this is the sparsity pattern of the matrix after pruning. We can see that it clearly has a banded structure. So if we count, there are exactly 28 bands, and each band have exactly 28 pixels. So why is it like that? And also it is white here and also white here. So why is it like that? Because if we see the data set, all the digits are mostly written in the center of the image. So on the peripheral, say here and here, here and here, there's nothing in the image. So the connections, so pruning automatically finds that those connections that connect with these empty parts are useless, so that it can be safely pruned. So this part corresponds to the first three horizontal pixels. First line, second line, third line, they are mostly white. And then these empty entries corresponds to after at the beginning and the end of when we scan the image, these parts are empty. And finally, these empty parts corresponds to the bottom of the image that are mostly empty. So that this figure, this visualization can show that the pruning mechanism automatically finds the important connections that we need to preserve in the image. So it not only learns the weight, but also learns the connections. Not only learns the weight of the connections, but also learns which connections are right to preserve in the neural network. So above, we talk about the applications for image recognition. So how about, those are convolutional neural networks. How about recurrent and recursive neural networks and RSTMs used in natural language processing? So this experiment works on the neural talk, which is done by Audrey Karpathy upstairs. And then it's an application of, the application is doing the image captioning. So I give you an image and let the neural network generate the caption of the image. So we can see that with no retraining, the blue score begins to drop. And with proper retraining, the blue score can be preserved until we remove 90% of the connections. So it's really interesting to see that about 90% of the connections in neural talk are redundant and can be safely removed and also preserve a very good performance. So let's see these examples. So for the first picture, the original network predicts the caption to be a basketball player in a white uniform is playing with the ball. And if we prune away 90% of the connections, the network produces the result saying that a basketball player in a white uniform is playing with a basketball. So it's even more accurate than ball. And how about the second one? The original network says a brown dog is running through a grassy field. And the prune network say that a brown dog is running through a grassy area. They're almost the same. And for this one, the original network says a man is riding a surfboard on a wave. And if we prune away 90% of the parameters, it says a man in a white suit is riding a wave on a beach. So this seems like something like a beach, although not a beach, I think. Something yellow. But if we are too greedy and prune away too much parameters, the network becomes drunk, totally drunk. Not totally drunk, but a little bit. The original network says a soccer player in red is running in the field, and the pruned network says a man in a red shirt and black and white black shirt is running through a field. It's not logically correct, but we can see there's still white, black, and red shirts. So this shows that the pruning also applies to not only CNNs, but RNNs and RSTMs. So just now we see the function and performance. What about the speed up? So I experimented with the FC layers of AlexNet, VGGNet, and NeuroTalk, and on 3 different platforms: the Intel i7 CPU, the NVIDIA GTX Titan X GPU, and also the NVIDIA TK1 mobile GPU. So I experimented with both the dense network and the pruned network and compare their speeds on 1, 2, 3, 4, 5, on 9 benchmarks, and this is the geo mean. So if you see the average, so on CPU, the pruned network is roughly 3x faster than the unpruned network. And on the GPU, it's also roughly 3x faster than the unpruned network. And on mobile GPU, it's roughly 5 times 3 divided by 0.6 faster than running on the unpruned network. So there are some cases where there's no speed up. For example, this one on CPU, the VGG8. So this layer is already small enough that even it has a size of 4K by 4K. So it's already 4K by 1,000, sorry, 4K by 1,000. So the unpruned network is already small enough to fit in cache. So the pruned network also, even got pruned, it still fits in the last level cache. So the speed up is not very significant. But if you see those large layers, say VGG6, it has as much as 9 times speed up on the CPU because the pruned network can fully fit on the L3 cache, but the unpruned network cannot. Some details. The unpruned network is implemented on CPU is implemented with MKLC plus GMV, and the pruned network is implemented with CSR MV. And similarly, on GPU, the pruned network is implemented with the CU sparse library, cuSparse, and the unpruned network is implemented with this cuBLAS. So what about the energy efficiency running those layers? So on average, if you see here, on the CPU, it roughly takes 6 times less energy, and on GPU, it takes 3 times less, and on mobile GPU, it takes roughly 4 times less than the unpruned network. Okay, so talking about pruning, we switch gear to quantization and weight sharing. So quantization and weight sharing are implemented with this method. So we first cluster the weights by, say, k-mean clustering, and then we generate the codebook, and then we quantize the weights according to the codebook. And finally, we retrain the codebook and iteratively do this process. And by reducing the network by another 27x to 31x, we can preserve the same accuracy by proper retraining. So what is the retraining like? If we see this picture, it is a 4x4 matrix. And the weights with the same color are quantized with the same value. Say, if this weight is 2.09 and that weight is 1.92, then they are both quantized to 2, and then having an index of 3 pointing to this location. So when doing updates, these are the gradient generated by, say, Caffe. And then this gradient is grouped by the index. Say all the weights with the same color are grouped with the same row here. And then they are reduced by summing these gradients together. And then finally, these reduced weights are multiplied with the learning rate and minused by the original centroid weights. And this concludes one iteration of the updates. So what is the benefit of this? So let's see what exactly do we need to store previously and now. Previously, we need to store all these 16 weights. Each weight, if it's a floating point number, that's 32 bits or half bit or 16 bit. Now we only need to store the four numbers, the centroids, plus the index. So in this case, the index can be represented with only 2 bits instead of previously 32 bit. And the code book has only 4 entries, but this is still using the 32-bit float. So if you see a real distribution of the weights on AlexNet, so these are the weights after pruning and retraining. We can see that everything that's close to 0 has been eliminated after retraining. So it roughly forms a bimodal distribution. So the green dots here, green crosses here are the initialization of the centroids. But after clustering and fine-tuning, the weights, the codebook, are those red dots. So those millions of connections here can be represented in only these 16 dots, only these 16 red dots to represent the original network. So for example, the FC7 layer of AlexNet has 16 million parameters. But now you have to only store 16 parameters and their indexes. So that's a huge saving. So in this year's NIPS, there's another work doing even more aggressive quantization by making it only 1 bit, so +1 and -1. They show their result on Amnis dataset and Cypher dataset, but I'm really looking forward to their result on the ImageNet dataset as well. But this figure roughly shows the shape of, say, this is +1 and this is -1. The shape is very similar. So the result, so 60 million parameters, now you can have only 16 parameters. So if we have 8 5-bit quantization, means conv layers represented by 8 bits, FC layers represented by 5 bits. There's no accuracy loss on ImageNet dataset. And 8 4-bit quantization, which is a little bit more hardware friendly, 2 4 bits or 8 bit, which is a byte. There's only 0.1 top 1 accuracy loss, which is kind of negligible. And then if you want to be more aggressive, so if you are really limited by a hardware resource, and you don't care a little bit of accuracy loss, say 2% or 2.6%, you can more aggressively compress it to only 4-bit or 2-bit for the network. So those results are astonishing. Let's see the detailed breakdown of each layer of the AlexNet. So the x-axis is the number of bits we preserve. Say this is 8-bit, 7, 6, 5, 4, 3, 2, all the way to 2 bits. And the y-axis is the accuracy, the inference accuracy. So if you see the conv layers, not until the 3 bits or 4 bits does the accuracy begin to drop. And for the FC layers, not until 2 bits does the accuracy begin to drop. So this shows that there's a lot of redundancy in the network. And just now we have seen both pruning and quantization. So these two methods both reduce the model capacity and the size of the neural network. So one question that we may have is, can they work together to further bring down the size of the neural network? The answer is yes. So let's see these 3 figures on FC layers and conv layers and all the layers. And this is the top 5 accuracy, and this is the top 1 accuracy. So there is a dashed line and a solid line, meaning both pruned and quantized network, and the quantized only network showing in let's see this one, showing in dash. We can see that this solid line works even better than this dashed line, meaning that the quantized and pruned network works even better than if you quantize the network only. So why is it like that? If we see the distribution here, pruning, which is make the distribution in blue like this, already roughly quantize the network into binarize the network. Say this is one group, this it's low power. This is one group, this is another group. So it already helped the quantization a little bit. And furthermore, pruning reduced the number of connections that you have to quantize. Say previously you have 10 million, or you have 16 million parameters to prune to quantize. Now you only have 1 million parameters to quantize. That makes the quantize even easier. So that's why pruning and quantization can work very well together. So lastly, so the final step of the compression pipeline is Huffman coding. So this is a lossless compression technique working on both the weight and the index. And the motivation is that both the weight and the index are biasly distributed. So if we can represent the weight that occurs more frequently, say this one, and use more number of bits to represent the weight that doesn't occur very frequently, use very little bits here, and use a variable length of bits of representation, it can further bring down the model size. Although this method uses Huffman encoding and Huffman decoding in the inference stage, so I did not implement this one in hardware, but implemented in the compression software. So if we apply the whole compression pipeline, the pruning, quantization, and Huffman coding, we can compress the network. These 4 networks ranging from 35 times to 49 times without increasing the test error for all these cases. So here's a comparison of different methods. So the x-axis is the compression rate. Say here we compress the network by 5% of its original size. And this one shows the accuracy loss. So if we apply both pruning and quantization, the network can be compressed all the way down to around, say, 3% of the original size without losing accuracy. But if we apply pruning only, it begins to, and also quantization only, the accuracy begins to drop when it's compressed about 10% of its original size. Furthermore, if we apply the relatively cheap SVD, the singular value decomposition technique, to approximate the matrix, we can compress the network by only around 20%, then the accuracy begins to drop here. So the thing that works best is the pruning plus quantization, the red line here. So here's a detailed breakdown of different layers on the left-hand side of the AlexNet. So with the whole pipeline is compressed to 2.88 of its original size. But without Huffman coding, it's still compressed to about 3.7% of its original size. And the layers are presented with 8 bits for conv layer and 5 bits for the FC layers. So here's a comparison with other published compression methods. So the pruning plus quantization plus Huffman coding worked best compared with other compression methods found on the literature. So here's a conclusion of deep compression. So we have presented a method to compress deep neural networks without losing their accuracy by first pruning away those unimportant connections and then quantize the network and enforce weight sharing, and finally apply Huffman coding. The network can be compressed by 30 times x, ranging from 35x to 49x without losing the accuracy. So now all the weights can fit in cache and can motivate us to build a specialized hardware accelerator that works on this compressed model. If we think of the compressed model, it is a sparse model. It has indirect lookups, which is not that hardware friendly on those customized hardware. That's why later I built a hardware accelerator that works on the compressed model. And by the way, as a product, we are going to build a model compression tool for developers if you're interested. So we're going to produce two versions, an easy version. So no retraining is needed. It's very fast. Can have around 5 times to 10x compression rate, and given about 1% accuracy loss. And we're going to produce an advanced version, which have 35 times to 50 times compression rate with no loss of accuracy. But training is needed. It requires some training time. And this is a demo of AlexNet, Pocket AlexNet, that's very small, that you can put it in Pocket. That's why I call it Pocket AlexNet, roughly only 8 megabytes. So with the compressed model, the next step of my work is to build a efficient inference engine that works on the compressed model to give even larger speed up and make it even more energy efficient by building a specialized hardware accelerator. So this is the hardware accelerator we're going to build. So it has 3 features. First of all, it's running offline. You don't have to upload your image to the cloud. And then it's real time, no network delay, and high frame rate. And finally, low power, has high energy efficiency that preserves your battery. So how do we achieve those 3 goals? So the main motivation and the main solution is put everything on chip. So previously, we have seen that picture that memory reference is really expensive compared with other operations like ALU operations and cache access and everything else. It's 2 or 3 more order of magnitude than those operations. So after compression, everything can completely fit on chip so that you don't have to go to off chip to fetch those parameters from DRAM. So that gives you both speed up and energy efficiency. So we present a sparse, indirectly indexed, weight shared matrix vector accelerator that accelerates the compressed model, the F series of the compressed model. Now the large DN models can fit on chip SRAM, which is 120x energy saving than going to DRAM. And then the EIE, efficient inference engine, exploits the sparsity of the activation as well, since after ReLU operation, the activation also becomes sparse. Lots of them are 0. So if we don't do computation on those 0 activations, we can save another 3 times computation time. And also EIE works on the compressed model, which, without Huffman coding, is 30 times model reduction compared with the original model. So you do less work. So you do 30 times less, fetch 30 times less parameters. And for each parameter, you save 120x energy. So for the accelerator, I distributed both the storage and computation across multiple PEs so that you can scale your system with your application. If your application needs a large network, then I have a lot of such PEs. But if you have a small, seen from this picture, if you have a large network, I have more PEs here. But if you have a small application with a small model, I can only have 4 PEs so that you can scale your system with your problem. And finally, we evaluated EIE on a wide range of deep learning models, ranging from CNN for object detection, RSTM for natural language processing and image captioning, and also compared with GPUs, CPU, GPUs, and other ASIC accelerators. So this figure shows how do we distribute the storage and processing across different PEs. So showing this figure, this is a matrix in a certain hidden layer of a deep neural network. And the weights, you can see there are a lot of zeros corresponding to we have pruned network, so that a lot of them are zeros. And a lot of them, so the weights with the same color are stored in the same PE, so that it's distributed and partitioned in the row manner. So this each PE can process its own part. It does a local reduction without too much communication with other PEs while you process a single element. And then inside each PE, it goes through these 3 steps. So first of all, the input of the engine is the compressed deep neural network model and the input image. And so that we store the encoded weight in SRAM, relative index in SRAM, with a sparse format. And then we fetch the 4-bit virtual weight and the 4-bit relative index. Remember, this is only 4-bit compared with the original 32-bit floating point or 16-bit half precision floating point. And then for the weight, we do a weight lookup. And for the index, we do an index accumulation since it's a relative index. And then we get the real weight and the absolute index so that we can use the real weight to do ALU operations, and then use the absolute index to fetch the code, fetch the parameter from the codebook. Finally, we do the prediction and get the result. So this hardware accelerator is evaluated with the standard ASIC design flow. So first of all, we build a secure, accurate C++ simulator that has 2 abstract methods, propagate and update. So this simulator is used for design space exploration and later served as a golden model for the verification of the Verilog. And the next step with the simulator, we have a RTL written in Verilog that we have verified its output with the golden model in model sim. And next step, we synthesize the EIE using the Synopsys design compiler under the TSMC 45 GP library, which we used standard VT library with the worst case PVT corner to make sure everything works correctly. And finally, we placed and routed the PE using the Synopsys IC compiler, the ICC. And we used the cacti to get the SRAM area and energy numbers. And in order to get the power consumption, model the power consumption, we have annotated the toggle rate from the ITR simulation to the gate level net list. Remember, the power consumption is, the equation is CV square and times frequency. So we need, we can get the capacitance from the post layout libraries, the libraries from the post layout circuit. And V, we can get it from the library as well. And F, the frequency, we have to get it from the simulation result, which is annotated with dumped into a switch activity interchange format, the SAFE format, and estimate the power using the prime time TPX tool. And then we baselined the hardware efficient inference engine on these benchmarks, which is ranging from AlexNet VGGNet and NeuroTalk, and run it on compared with CPU, GPU, and mobile GPUs. And this is the layout of our chip. So this is the SRAM that stores the sparse matrix, and this is the SRAM that stores the pointers. And the inside here is the meat, which is the arithmetic unit. So as we can see, still most of the chip area is consumed by the SRAMs. So under TSMC 45 nanometer, it consumes 9 milliwatts for each PE and taking an area of 0.6 millimeter square. And the critical path of the engine is 1.15 nanometers. So 48 such PEs is large enough to hold AlexNet. So you can scale the number of PEs with your problem size. So without model compression, we cannot fit all the parameters on those SRAMs. But only with model compression can we fit everything on chip. That's the merit of EIE. So let's see the speed up and the energy efficiency of EIE. So this is the speed up, and this is the energy efficiency. So across different benchmarks, the right-hand side is the average value. So previously we have seen these bars. Now we have a new bar here. So we can see that the EIE engine, which is in red, is 189 times faster than CPU running the uncompressed model, and is roughly 18 times faster compared with the GPU with running the uncompressed model. And with respect to the energy efficiency, the red bar, which is EIE, is 24,000 times compared with the CPU running on the uncompressed model, and is roughly 3,000 times more energy efficient than the GPUs running the uncompressed model. So where does this number come from? The 3,000 times more energy efficient than than the GPU. So if we do a hand calculation, so by compressing the network, we can save around 30 times of, we can have 30 times less model size and less parameters to fetch from either SRAM or DRAM. And then since we compress the model and everything fits in SRAM, the SRAM is another 120 times more energy efficient than fetching from DRAM. And remember, we can utilize the sparsity of the activation, which is roughly 3 times sparsity. So all the way, there is roughly, if you do the calculation, it's roughly 10,000 times more energy efficient. But this is using 45 nanometer technology, and the GPUs are done, GTX Titan X is done in 28 nanometer. So divided this number by 2, we get roughly 5,000 times. Theoretically, 5,000 times more energy efficient. But probably we didn't do it good enough. We're going to get 3,000 times. So let's see the speed up by benchmarking with the CPU, GPU, and mobile GPU. So these are those are really small numbers, but different benchmarks with different batch size. So this engine is targeting real-time processing, which the numbers are the previous figure are generated using batch size of 1. So during, say, self-driving car, you don't have the time to batch 64 images and wait until 64 images to come and process them together. That's why we use batch size of 1 to do the benchmark. So this figure shows the scalability of EIE, ranging from 1 PE all the way to 256 PEs. So the scalability log scale is roughly linear speed up, except for this one. So the neural torque WE, this matrix is really small. So with 256 PEs, considering the sparsity, each PE has around just one element to process, so that when there are a lot of PEs, it does not grow that much for this benchmark. But for the rest, the scalability is really good. And this figure shows the number of useful computation on the top across different PEs, and also the load balance with the different number of PEs. The useful computation, some of them is not 100% because with the relative index, we have to pad zeros. If we cannot use 4 bits to represent the jump, we have to pad a dummy 0 over there so that the useful computation is less than 100%. But with more PEs, the more PE we have, the less padding 0 we need, so that the useful computations becomes more. And this is analysis of the load balance with more PEs. So the more PEs we have, each PE will have less number of parameters to process. Thus, it's highly possible that some PEs have 3 parameters, some of them have 8 parameters to process, leading to temporary load imbalance. So how do we deal with this? So we introduce the FIFO queue that decouples the computation between different PEs. So we have a couple of different sizes, 1, 2, 4, 8, 16. We experimented with different FIFO size to see the load balance feature of the EIE engine. We can see that the load balance becomes pretty well when the FIFO size is roughly of size 1, 2, 3, 1, 2, 4, 8 here. And after a size of 8, the gain became, the benefit becomes marginal. So we choose, in the design, we choose the FIFO size to be 16 here. And here's more design space exploration of the EIE engine. So on the top, this is the design space exploration of the SRAM width. So the wider the SRAM, the less number of read shown in green we need, but the more energy it takes reading each parameter. But if we multiply them together, we'll see the total energy. We can see at 64-bit, the width of the SRAM gives the most efficient usage. So we choose the design of the SRAM width to be 64-bit. And also we have analyzed the arithmetic precision after the quantized weights. So so in the code book, previously, remember, we quantized all the weights with the code book so that 16 million parameters became only 16 parameters. And those 16 parameters, how many bits do we use to represent the weights play a larger role in the energy efficiency? So we can see that the 32-bit floating point multiply takes roughly 4 picojoules. But a 16-bit integer operation takes roughly only half a picojoule, which is a lot more efficient. And then we experimented with the accuracy from 32-bit float to 32-bit int to 16-bit int. And we can see not until using 16-bit integer does the accuracy begins to drop. With the 8-bit integer, the accuracy becomes unusable. So that we choose the arithmetic precision of the codebook to be 16-bit integer operation. So the EIE engine has recently been covered by the Next platform, titled Emerging Chip Vastly Accelerates Deep Neural Networks. And if we see the big picture, if we say that Intel defined the chips that does computation in the PC era, and then Qualcomm and Samsung and Huawei and those companies defined the mobile computation in the mobile era, then what is the next generation of chips that defines the era of the intelligent mobile computation? And I hope that deep learning hardware for deep learning such as EIE can shed some lights and give some interesting motivation and pave the way for future chips that target intelligent mobile computation. So here's a conclusion of my talk. We presented EIE, an energy efficient engine optimized to operate on the compressed deep neural network, which is done by pruning, weight sharing, and Huffman coding. By leveraging the sparsity in both the activations, since we have redo activation function, and the weights, EIE reduced energy consumption of typical FC layer by 3,000 times. And this is the breakdown of where does this 3,000 times come from. So first compression, and then DRAM to SRAM, and finally sparse activation. That's my talk. Thank you for your attention. And I'm glad to take questions. Yep.
Yes, did you consider generalizing your matrix vector representation into a tensor?
Into a tensor. So currently it deals with single matrix vector multiplication with batch size of 1. Currently it does not support tensor operation at this moment.
So once you've done the pruning, of course you can't train on a different training set because it might have outliers that would have put substantive weights on the links that you've removed, right?
Sorry, what's the question?
So if I wanted to train on a different training set, and it would have not made 0 weights on some of the links, but once you've pruned them, it's all gone. You can never put a weight there because there's no link, right?
Right. Say, as we see from the digits, unlisted data set, if the digits are written on, let's say, the left-hand side of the image,
exactly.
You have to re-prune the network and have a different pattern.
But for example, in speech recognition, they're always improving because they're continually retraining based on continual input. Might that not lead to positive weights where you've pruned the link?
If you prune a link with as the new, it should be a new problem with say online learning when you constantly have different data sets.
Yeah.
then you cannot fix the pattern of the pruning mask. Yeah.
How many of those systems actually iteratively train anyway? So, how many learning systems, deep learning systems, do iterative training anyway?
So the speech recognition systems, even Dragon, is quite good when you start, but it gets better over time.
But do they iterative? Do they?
I don't know.
I don't know. Or they rerun?
I don't know.
Yeah.
I'm just saying, but it seemed like, his example, if another training set had the figures left justified instead of centered, then you wouldn't get the right weights.
Yeah, so this is targeting, say, you have a very well-developed model, and then you want to actually deploy it.
So that's my answer.
Yeah, so from what I said, the key feature is that you're compressing the network and make it fit inside the cache, right? So it raises 2 points. What if after compression, it doesn't still fit in the cache, or there's a new technology that makes DRAM, or let's say the memory, as efficient as SRAM? Would I still need to do compression or not?
So if you see the equation here, there are 3 terms. If your DRAM is SRAM is large enough that can hold a lot of parameters, you can lose one of the terms here, but you still have the rest of the terms, I think. And then generally, if you have an app, if you build an app writer, and you want to have your app on the App Store, you want a user can download your app very fast, then you still need to have a relatively small app. Just depends on the game. If the hardware continues to say in one day you can have a really, really large DRAM or SRAM, then probably will doesn't need those really aggressive compression, but compression can still gain you something, maybe not that much, 3,000 times, but maybe say 300 times. Yeah. That's right.
So you saw the comparison with SVD, approximation to the wave matrix, right? You can, to compress. And when you did SVD, did you retrain on the SVD?
For
In other
that
words, you can retrain those single vectors to move them around.
Oh, in that one, that's a simple SVD. I didn't retrain the singular vectors.
Okay, so do you know how well that would do, or?
Given the, it's not. I also tested with not retrain the pruned model, and not retrain the quantized model, and seems like even without retraining, it's less optimistic if you just do the SVD. It's already begin to fall pretty sharply when you decrease the model size. And there's a detailed paper about SVD published in, I believe, in NIPS last year by Facebook. And so advanced version of SVD. Yeah.
Thanks for a very nice talk. It's very good work. I'm wondering, so like when you're pruning, you're typically, the biggest savings comes from the fully connected layers, right? Because that's where all the weights are. But a lot of these Convnets don't actually use fully connected layers now. They just have convolution layers all the way through. So it's almost like they pruned up front to begin with, and then they trained, and already the network's 30 times smaller, and they still get very good results. So do you think it's the pruning's important, or just removing those connections up front?
I think the structure compression is a really good thing. For example, the Google Net, which is really, really small. And then I exactly have the same thinking when I visited Baidu. So they have a face recognition network that almost all the layers are conv layers and only have one FC layer. And they still using my technique to compress their model by 10 times to make it even smaller to put in Baidu's face recognition app. So I think the final solution I appreciate most is applying both methods. So first the structural compression, and then those deep compression techniques I described to make it smaller to have to the limit. Any more questions? Cool.